installment of GlasgowTea, so we're up and running now. Just some general housekeeping. Keep your microphones off. Put your camera on if you want. We are recording, and this is going to go on our YouTube. Usually, this would be hosted by the lovely Rachel Taylor, but she is off on her honeymoon this week, so she has tasked me. Because honestly, I'm just behind the scenes. Rachel does almost everything, so it's my responsibility this week. So we will miss her. But thank you so much for joining us. Today we have a speaker, Max Primbs, who is going to be speaking about data pre-processing and multiverse analysis. I'm going to be honest, this is the one I feel most out of my depth with so far. So I'm really excited to learn a little bit more. Just for a little bit of a bio, Max is a second-year research master's student, and he is soon to be a PhD researcher at Radboud University, so congratulations. He is interested in bias, implicit bias, stereotypes, and open science. Another interesting fact is he is the Assistant Director for Translation and Cultural Diversity at the Psychological Science Accelerator, which I had to Google to understand more about what it was. And it is a globally distributed network of psychological science laboratories in 71 countries that coordinates data collection for democratically selected studies. So really, really cool, really focused around standards and best practice of translation procedures and cross-cultural research. So that's really, really interesting for me. I think that's amazing, Max. And I am really, really looking forward to this talk. So I am going to be quiet and pass over to Max.
Okay. Hi, I'm Max, and I'll talk to you today about data pre-processing and multiverse analysis. But before I start with data pre-processing, I want to explain the paradigm of which I will use as an example throughout the talk, so you have a better idea of what type of data it is and what participants in these paradigms usually see. Next slide. Yes. So the paradigm is called breaking continuous flash suppression. It is a reaction time paradigm, and it is used in consciousness and perception research. And it allows you to measure how much time passes between the initial presentation of a stimulus and the time a participant reports seeing it. So as a measure of detection time. And watching things is always easier than listening, so we prepared a short video. So as you can see in the video, in BCFS, participants are seated in front of a computer screen. There are two squares on the screen, and their head is fixated on a chin rest with a divider between their eyes. One of the two squares will always contain the target stimulus, and that can be a face, that can be a number, that can be whatever visual stimulus you can think of. And the other square will always contain a so-called Mondrian pattern, which is a constantly changing, very colorful pattern. Now, because our brains are weird, and because each eye only sees one of the squares because of the divider, participants don't in fact perceive two squares, they perceive one single square. That means in the participant's vision, this colorful pattern and the target stimulus overlap. And the idea behind this BCFS thingy is that the colorful pattern attracts all of our initial attention and mental resources. And thus, initially, we only see this colorful pattern, and only over time we have the target stimulus breaking through. Now, using this paradigm, and now we're getting started on data pre-processing, one group of researchers found that we can prime mathematical equations unconsciously, and apparently also solve them unconsciously. So in a series of experiments, Sklar and colleagues first primed participants with a mathematical equation, and then presented them with numbers using this BCFS paradigm. That means they measured the time participants required to detect that number. And what they found is that participants were faster to detect numbers which were the solution to the mathematical equation presented earlier. From that, they then concluded that people solved this arithmetic equation and therefore expected to see the solution there. So their brains were prepared to see this, and thus they were faster when they actually saw it. Now, of course, they claim we can do math unconsciously, is very big, and people try to replicate that finding. There were two notable replications, one by GlasgowTea and colleagues, which failed to replicate this effect, and one by Kapinski and colleagues, who successfully replicated it. Both replications underwent a lot of scrutiny, and then after about 2 years, the authors decided to retract their article because somebody found a coding error in the successful replication. And after a correction of that coding error, the effect was no longer significant. Now, in an ideal scientific world, this would be the end of this short excursion, but the authors published the same paper again 2 years later, now again proclaiming to have found a significant result. Of course, a lot of people were baffled by how that was possible, and a very close look at the methods and results section gives away the answer. Kapinski and colleagues sneakily changed the inclusion criteria for participants in individual trials. That means, effectively, they changed the data in the study and then again proclaimed finding a significant effect. While I personally find that to be very questionable, that's not the point I'm trying to make here. What I do try to show is how these very small decisions we all make every time we analyze our data can have potentially massive implications for our results and conclusions. So in a recent project, I tried to investigate these effects of these data pre-processing decisions more systematically. And in this project, we asked two questions. First, we wanted to know what type of data pre-processing decisions people actually make. And second, we wanted to know if that even matters. So if different data pre-processing pathways reliably produce different results. And this project was together with Kai Spalster, Rob Holland, and Julian Quant. So to answer the first question, how do people pre-process their data? We conducted a survey of all published papers using this BCFS paradigm, and then checked how they pre-processed their data and which analysis they ran. This first graph simply shows on the x-axis the type of analysis, and on the y-axis the count. And as you see, most people really like running simple tests like frequentist, t-tests, or ANOVAs, whereas only small minorities employ mixed models, Bayesian models, or other more complicated models. And in total, we surveyed 101 papers. Now, on the second graph, I additionally to the analysis used, coded which type of data transformation people used. So reaction time data is often very skewed, and many analyses assume some sort of normality of either residuals or difference scores. So people often use transformations to make the data fit the assumptions of the test you're going to use better. The reddish proportion here corresponds to raw data, so to no transformation used, and the greenish proportion corresponds to the log transformation. So what you can see is that most people use tests which assume some sort of normality, but they don't make their very not normal data more normal. You can also see that with just these two decisions coded, there are already 13 unique pathways across our 101 papers. Now, reaction time data often has a lot of outliers. And in this graph, I additionally coded if outliers were removed, as yes or no. And with the decision analysis, data transformation, and trimming yes or no coded, we're already at 20 unique different combinations across our 101 papers. But of course, not everybody removes outliers the same way. You can remove outliers based on means and standard deviations, on interquartile ranges, on fixed limits, or on median absolute deviations. There are a lot of options. And if we code all the options used in the BCFS literature, we now arrive at 46 unique strategies across 101 papers with only 3 decisions coded. And of course, you could code many more than only these 3 decisions. You could code the exact value used for outlier exclusion. For example, 2 or 3 standard deviations from the mean. You could also code how exclusions were handled on a participant level. Short, if you would code every aspect of the data preprocessing pathway used in these papers, you would probably end up with about as many pathways as there are papers. And that's honestly quite sad. How can science be truly cumulative if everybody is doing something different? So next, we wanted to know if these differences matter. And for that, we took 10 data sets investigating the in-group bias in face detection and pre-processed it in 6 different ways. The in-group bias in face detection is simply the finding that people who grow up in less diverse places where most people have the same skin color are faster to detect faces of the same skin color. So white Dutch people are faster to detect white faces than, say, Moroccan faces. And Chinese people who grew up in China are faster in detecting Chinese faces compared to Caucasian faces. Now, after we pre-processed these 10 data sets in 6 different ways, we analyzed these 60 combinations with 3 different analyses, resulting in a total of 121 combinations. And the analysis we used were a frequentist ANOVA, a Bayesian ANOVA, and a robust meta-analysis. So what did we find? On the y-axis, here you can see the median F statistic across all 10 data sets. On the x-axis, you can see the type of pathway. The first orange bar and the white spot next to it hereby correspond to pathways based on the raw data. The second orange bar and the white spot next to it correspond to analysis based on log transformed data. And the third orange bar and the white spot next to it correspond to analysis based on latency normalized data. And the orange bars are simply pathways where outliers have not been removed. So what you can see is that data transformation increases your F statistics, and larger F statistics with the same sample size means smaller p-values. So by transforming your data, you're more likely to find significant results. Now, the blue bars correspond to pathways where outliers have been removed. And you can see that for raw data, removing outliers increases your F statistic, and for transformed data, it decreases it. And this pattern becomes much more obvious if you look at the Bayes factors, because Bayes factors are scaled differently than F statistics. So the differences are much larger or appear much larger for Bayes factors. Again, data transformation increases the Bayes factor for untrimmed data, whereas removing outliers increases the Bayes factor for raw data, but decreases it for the transformed data. Now, if you have a very sharp eye, you maybe have seen that on the y-axis, we have the log of the Bayes factor and not the raw Bayes factor. And that is because if you plot the raw Bayes factor, it looks like this. To put it in words, the difference between the most commonly used pathway based on raw and untrimmed data and the latency normalization pathway is 569. So by making the small decision to apply a transformation to your data, your average Bayes factor across 10 data sets goes from 3 to 572. Similarly, if you make the small decision to remove outliers, this Bayes factor of 572 is reduced to 80. Now, usually if you aggregate across data sets, you don't use F statistics or Bayes factors. You use meta-analysis and standardized effect sizes. So we also conducted a robust meta-analysis based on Cohen's d. And what we find is similar to the results of the individual analysis. The data pre-processing pathway matters. The estimated effect size for the normalized data is 4 times as large as the estimate for the raw data. And here, removing outliers even further increases the effect sizes. On a first glance, here the effect of trimming increasing the effect size may be counterintuitive given the earlier results, but Cohen's d is just the mean difference divided by the pooled standard deviation. So when you trim data, you reduce the standard deviation, and the mean difference remains mostly unaffected. So you will always increase your effect size. Now, I have talked enough for a bit, and it's time for you to do some work on your own and experience the effects of data pre-processing for yourself. So together with my friend Leonard Waltz, I programmed a Shiny app that allows you to explore the effects of data pre-processing. In the Shiny app, you are presented with a simple data set consisting of 2 groups and its reaction time data. On the left side, let me see if I can, no, I can't. Yeah, on the left side, you can vary different preprocessing options. You can vary the transformation you use, you can vary fixed limits, trimming, and you can vary data-based trimming, such as median, standard deviation. On the right side, you then have several outcome statistics, including density plots, summary statistics at a trial and participant level, and the results of a t-test. Now, what I want you to do is to try out different settings and try to find the lowest p-value you can find. And if you found a very low p-value, I want you to note down your settings. And Rebecca just posted the link to the app in the chat. So you can all open it. It takes a second to load because it's on the free Shiny servers. And then we take about 5 minutes for you to find the smallest p-value that you can. And afterwards, we're going to look who of you is the most gifted in data preprocessing / p-hacking. If you have any questions, you can ask now. And the app also has a help function, which tells you what the different data preprocessing options actually do.
Hi, yeah, just let me check again. So can you hear me first off?
Yes, we can hear you.
So I use the square root transformation to normalize the data a bit, but I used it not on the raw data. That seemed to be important, so I unticked the trim based on raw data. And then I trim both the minimum and maximum based on the MAD set at 3. And that seemed to kind of make my standard deviations the smallest they could be.
All right. And if you also have a look at the chat, you will see that there are 3 coinc with a minus, so indicating an in-group effect. But Rebecca found an equally large coinc in the opposite direction, which is also highly significant. So just by choosing different options, you got vastly different estimates, even in different directions, with relatively large standardized effect sizes. So what I want you to remember from this first part of the talk is that there are many, many different analysis and preprocessing pathways, and that different pathways can produce wildly different results. And then the question, of course, becomes, how do you know which pathway is best? How do you select the right preprocessing pathway? And in principle, there are 2 types of approaches to do that. You can make decisions based on theory, and you can make decisions based on statistical justifications. For example, in reaction time paradigms, you usually assume that there's some sort of processing threshold. So humans are only so and so fast. So if a stimulus, for example, is detected after 50 milliseconds, that is faster than what most researchers claim the human processing speed is, which is about 200 milliseconds. So you could use this reasoning to say that you should implement a minimum threshold of, say, 200 milliseconds. Another question you can ask yourself is it plausible that participants take several seconds for a trial in my task? And if not, you can implement a maximum threshold. Now, statistical justifications could, for example, be, do I expect my data to be normal? For reaction time data, you usually don't expect it to be normal. So you could decide to make some justifications and then use data transformation. But that's not really often done in psychology. Papers making theoretical or statistical arguments for why certain data preprocessing decisions are better than others are very scarce. But I want to highlight one paper from 2021 by Quentin Andre, which did just that. And in his paper, Quentin, for example, compared the effects of removing outliers across all data points to the effects of removing outliers within conditions. And he showed that if you remove outliers within conditions, you change the distribution of your data in a way that priorly normal data is now no longer normal. And thus you inflate your alpha error rate. So the problem with that approach is that there are, as you saw in the app just now, endless amounts of different options which you can choose. And in his paper, he compares a few options, but there are so many more. And even if you somehow manage to find one best method, say the median absolute deviation from the median, how do you know if you want to use 2 median absolute deviations or 2.1 or even 2.034? I say you can't. And also you shouldn't. Why would you make decisions based on some flimsy criterion when you can alternatively just run all the pathways which theoretically and statistically are justified? If there are many pathways which fit the data, why choose? Just run all of them. And this running all pathways is in psychology called multiverse analysis. So it's a systematic evaluation of all possible and sensible combinations of the different options you have when analyzing your data. For example, different preprocessing decisions, or whether you want to exclude or include certain covariates, and decisions like this. I know this sounds a bit abstract, so we'll start by going through an example. In 2014, a paper by Young and colleagues showed that female hurricanes cause more death and cause more destruction than male hurricanes. And the authors argue that this is the case because female hurricanes are presumed to be less dangerous than male hurricanes because of societal stereotypes associating men more strongly with danger than women. That in turn, they argue, leads people to underprepare for the female hurricanes, leading to higher death tolls. Now, this paper was published in PNAS again, and it attracted lots of media attention, and also soon lots of scientific criticism. And a lot of this criticism was aimed at the fact that apparently already changing small details of the analysis, such as excluding outliers, reversed the effect and made it disappear entirely. So for about 1 year after publication of this paper, some group would write a comment to the paper where they lay out a different model which finds no effect or which finds an effect in the opposite direction. And then they would argue that their model is somehow better. And then the original authors would again reply with, no, our model is better because X, Y, Z. But the problem with that is that the people never agreed on which model they think is best because they all had their own reasons. They all had their own justifications. And most of these reasons and justifications were theoretically and statistically valid and sensible. And that's where multiverse analysis becomes useful. There are many different ways of which different experts say they are the right way. For example, without or without outliers, with or without certain moderators. So one team of researchers decided that they would end this discussion once and for all by running all the models. And here, by running all the models, I mean all the models. In their paper called We Ran 9 Billion Regressions, Munoz and Young, and that's a different Young, did just that. They ran 9 billion regression analysis, detailing all possible combinations of moderators, outliers, transformations, data exclusion criteria, and whatever else you can think of. Now, this graph here shows the summary results. The dotted line is the original finding by Young and colleagues from 2014. And you can see that this original study is at the extreme end of the distribution of coefficients. So it is an outlier. And you can also see that the peak of the distribution is somewhere slightly higher than 0. So if you only ran one single analysis, as the original authors did, you would have rightly concluded that you found strong evidence for gender bias against female hurricanes. But if you were another research team and you ran a model on the left tail of the distribution, you would also have rightly concluded, based on your data and your analysis, that there is strong evidence for gender bias against male hurricanes. And yet again, if you ran a model somewhere in the middle, you would probably have concluded that there's no gender bias in hurricanes whatsoever. And only by evaluating all pathways and looking at the distribution of effect sizes across different analytical decisions, you will have probably arrived at what could be the truth, or what is the best guess we currently have, that the gender bias by Young and colleagues was mostly an artifact of their model specifications, and that if a gender bias in the amount of destruction caused by hurricanes exists, it is very small. Now, for the next part, I want to briefly discuss different pitfalls you can run into when doing multiverse analysis. And these are based on a recent paper by Del Judis and Hangestad, where they discussed the concept of equivalence. If you run a multiverse analysis, you get different outcome test statistics. For example, an average p-value across all your preprocessing pathways, or the proportion of significant pathways, or the average effect size. But by taking the average, or by calculating these proportions, you implicitly assume that all of these specifications in your multiverse are interchangeable, that they are equivalent. And including non-equivalent or non-interchangeable specifications will distort the weight assigned to each specification and would thus lead to biased estimates. Now, there are three types of equivalence I want to briefly discuss. And the first type is measurement equivalence. In psychology, different constructs are not measured by one single indicator. For example, if you measure depression or social media consumption, there are 10 different questionnaires which can be used to measure depression or social media consumption. And each of these questionnaires or methods is differently well correlated with the underlying construct. So if you were to run a multiverse analysis with different outcome variables using different questionnaire scores, you would introduce bias to this multiverse analysis, because not every outcome or not every measurement of the outcome is an equally good measurement. The second type of equivalence I want to discuss is effect equivalence. That simply means that the effect of interest when running a multiverse should remain the same for all specifications in your multiverse. That sounds quite complicated, but it simply means that you should not include varying sets of covariates in your multiverse analysis. For example, the graph on the right shows a model of the effect of inflammation on depression. And in the model, age affects both inflammation and depression and is a confounder of their relationship. So if you run a model without age and compare it to a model with age, the model without age would automatically be inferior because it misses this confounding variable. So they would not be equivalent. The last type of equivalence is power or precision equivalence. And that simply means that some specifications can differ too strongly in statistical power. For example, if you run a multiverse on a data set which has 3,000 trials, and one of your specifications removes so many trials that you only have 400 left, then obviously the power to detect an effect will be very much higher in the 3,000 trial pathway than the 400 trial pathway. So they would not really be interchangeable. Likewise, as shown in the paper by Andre, some outlier criteria may be inherently worse than others. So by comparing them or by aggregating across them, you introduce non-equivalence. For the last 3 minutes, I want to discuss what you can do after you did a multiverse analysis. So what is the next step? Consider you ran a multiverse analysis and you ran 100 different pathways. And of these 100 pathways, 70 are now significant. What does that mean? How can you interpret this? What would be the proportion of significant pathways you would expect if your null hypothesis were true? You can't calculate that using normal null hypothesis testing because your data points are not independent. They are specifications based on the same data frame, and they are all differently correlated to each other. So one solution to that problem would be to use permutation testing. And permutation testing is a resampling technique which allows you to obtain p-values from multiverse analysis, comparing the observed data to data where the null hypothesis is true. And you usually take a 3-step approach for inference with permutation testing. You shuffle the independent variables, and then you just rerun your multiverse analysis. And shuffling the independent variables simply means that you break up all effects that might have potentially been in your data. And therefore, you create a data set where the null hypothesis is true by construction. And then when you rerun your analysis, you have the proportion of significant pathways which are significant in this data set where the null hypothesis is true. And then you can simply compare that to the test statistic of your observed data. And by repeating this process many hundred times, you can then see how many of these iterations have test statistics as large or larger than the observed data. And thus you get a p-value. Now, as a summary, there are many different analysis and preprocessing pathways, and they produce widely different results. To deal with that, you can run a multiverse analysis, which allows you to summarize evidence across many equivalent pathways. But the important thing here is that they are truly equivalent. And after you've done that, you can use specification curve analysis to draw formal inferences from this multiverse analysis. Thank you for the invitation, and I'm happy to answer any remaining questions for the rest of the time.
Yay. So now I'm going to stop recording before I don't, and I get all of our chat.